Hello, my name is Sangmin from KAIST, the first author of sketch-based video object localization. I will go through these contents. Query-based object localization and object detection share the common objective of identifying and localizing objects within an image or video through the use of bounding boxes. Object detection typically relies on predefined object classes to detect and locate objects. In contrast, query-based localization is grounded on the provided query, which can take various forms like natural language descriptions, images, sketches, etc. As a result, query-based localization is more flexible and adaptable to a wide range of user-defined queries and inputs, making it suitable for a variety of applications where specific objects or attributes need to be located in an image or video. Query-based localization literature have various query types and video domains. In the realm of query-based localization research, various query types and domains have been explored, such as image, language, and video. However, one noticeable gap in the existing literature pertains to the absence of studies focused on sketch queries in the video domain. We seek to address this particular gap in knowledge. We introduce a new task, sketch-based video object localization, aimed at localizing spatio-temporal object boxes within video content, with the query input provided in the form of a sketch. Sketch queries provide users with a high degree of flexibility, transcends barriers related to users' age, race, and nationality, and collecting sketch dataset have become more accessible and convenient than ever before. We propose Sketch Video Attention Network, SVANET, We propose Sketch Video Attention Network, SVANET. Inspired by DETR, we formulate SVOL task as a SPECSAT prediction problem and design SVANET. There are 4 components in SVANET. First, encoding pipeline. SVANET processes a video and a query sketch separately, generating frame representations and a sketch representation. Then, cross-model transformer takes these representations along with learnable object tokens and models interactions between objects, attending to sketch video joint representations to make precise predictions. During training, SVANET finds the best matching between predicted and ground truth sets for each video frame, allowing for the use of global video context in object prediction. In CMT, positional encoding is applied before attention operations, enabling it to emphasize significant content, learn correspondence between sketch and video, and transform object tokens into predictions of bounded box coordinates and objectness scores. We propose Sketch Video Attention Network, SVANET. Inspired by DETR, we formulate SVOL task as a set prediction problem. SVANET processes a video and query sketch separately, generating frame representations and a sketch representation. Cross-model transformer takes these representations along with learnable object tokens and models interactions between objects, attending to sketch video joint representations to make precise predictions. During training, SVANET finds the best matching between predicted and ground truth sets for each video frame, allowing for the use of global video context in object prediction. In cross-modal transformer, positional encoding is applied before attention operations, enabling it to emphasize significant content, learn correspondence between sketch and video, and transformer object tokens into predictions of box coordinates and object list scores. We will look into cross-modal transformer. It operates with a series of layers, each containing 4 attention operations. Sketch video cross-attention focuses on relevant video patches for accurate bounding box localization based on the input sketch query. Content self-attention models temporal relationships in the sequence of SVCA outputs. Token self-attention and content tokens cross-attention use object tokens as positional encodings, with token self-attention serving as a self-attention operation for object tokens, and content token cross-attention linking object tokens to contextual content representations. Each cross-modal transformer layer applies layer normalization and feed-forward networks to intermediate results. Positional encodings are added to enable permutation invariant attention operations. The final cross-modal transformer output is fed into linear layers to produce predictions for bounding box coordinates and object list scores, thus completing the object localization task. We will look into cross-modal transformer. It operates with a series of layers, each containing 4 attention operations. Sketch video cross-attention, namely SVCA, content self-attention, we will look into cross-modal transformer. It operates with a series of layers, each containing 4 attention operations. Sketch video cross-attention focuses on relevant video patches for accurate bounding box localization based on the input sketch query. Content self-attention models temporal relationships in the sequence of We will look into cross-modal transformer. It operates with a series of layers, each containing 4 attention operations. Sketch video cross-attention focuses on relevant video patches for accurate bounding box localization based on the input sketch query. Content self-attention models temporal relationships in the sequence of sketch video cross-attention outputs. Token self-attention and content token cross-attention use object bounding box. We will look into cross-modal transformer. It operates with a series of layers, each containing 4 attention operations. Sketch video cross-attention focuses on relevant video patches for accurate bounding box localization based on the input sketch query. Content self-attention models temporal relationships in the sequence of sketch video cross-attention outputs. Token self-attention and content token cross-attention use object tokens as positional encodings, with token self-attention serving as self-attention operations for object tokens, and content token cross-attention linking object tokens to contextual content representations. Each cross-modal transformer layer applies layer normalization and feed-forward networks to intermediate results. Positional encodings are added to enable permutation invariant attention operations. The final cross-modal transformer output is fed into linear layers to produce predictions for bounding box coordinates and object scores, thus completing the object localization task. We newly created sketch and video datasets. We created sketch and video datasets. We use ImageNet VID video datasets, and we use 3 different sketch datasets. The Sval dataset combines video datasets and sketch datasets for we created existing sketch and video datasets to create new Sval dataset. We use ImageNet VID dataset for video and sketchy TU Berlin quick draw datasets for sketch datasets. We combine these datasets to create we curated sketch and video datasets to create new Sval dataset. We use ImageNet VID video dataset and sketchy TU Berlin quick draw datasets for sketch dataset. We conduct quantitative experiments. We compare model performances on the Sval task using 3 different sketch datasets. We first compare SVANET versus image level baselines. We compare model performances on the Sval dataset. We compare model performances on the Sval dataset using 3 different sketch datasets. SVANET outperforms ImageNet level. We compare model performances on the Sval datasets. We compare model performances on the Sval dataset. We compare model performances on the Sval task using 3 different sketch datasets. SVANET outperforms image level baselines by considering both spatial and temporal aspects, significantly improving MIOU across sketch datasets. Among different model variants, the final SVANET demonstrates the best performance, highlighting the effectiveness of attention-based fusion. When using all 3 sketch datasets as a single query set, model performances slightly diminishes due to the greater diversity of sketch samples. Experiments revealed that 2D CNN outperforms 3D CNN, demonstrating the complementary nature of CMT in temporal modeling. We conduct 2 transfer tests. To assess the generalization capability of Sval system, we conduct 2 transfer tests. Sval to evaluate the generalization capability of Sval systems, we conduct 2 transfer tests. First, dataset level transfer. Small models are trained on one dataset and evaluate on another dataset with sketch. To evaluate the generalization capability of small models, we conduct two transfer tests. First is dataset level transfer, which to evaluate the generalization capability of small systems, we conduct two transfer tests in dataset level and category level. In dataset level transfer test, small models are trained on one dataset and evaluated on another dataset with style differences, such as line thickness and abstraction level. The transfer performance is significantly better than training solely on the evaluation dataset. This indicates that the model learns class discriminative features independent of sketch style differences. In the category level transfer task, models are trained on a subset of sketch categories and evaluated on unseen categories. Despite some degradation in performance, SVANET outperforms baselines in category level transfer, highlighting its ability to reason about implicit similarities and embed sketches of the same category closely in the feature space. The results suggest that small models operate based on key features, such as object-specific details, rather than relying solely on overall visual appearance, indicating the importance of implicit similarity for accurate object localization. To understand the behavior of cross-modal transformer, we visualize its attention maps. Here, the brighter the color, the higher the attention intensity. Sketch video cross-attention highlights areas that align with the actual locations of sketch object, showing its ability to determine where to look. Content self-attention captures deeper correlations between temporally adjacent sequences when modeling temporal context, enhancing its understanding of temporal relationships. Content token cross-attention provides a when-to-look aspect, offering temporal inductive bias for object tokens when combined with per-frame sum matching. This is our qualitative results. This is another qualitative result. This is failure cases. So we summarize our contributions. First is new task. We introduced the challenging task of sketch-based video object localization and identified associated challenges. We created a new usable dataset by combining video and sketch datasets with different styles and provide a benchmark with comparisons against frame-level baselines and model variance. We propose SPANET, a novel framework tailored for SPOL, serving as a strong baseline, significantly outperforming existing models on benchmark datasets. We conducted comprehensive ablative studies on model components and demonstrated the generalizability of SPANET on unseen datasets and novel categories, making sketch-based queries practical in real-world scenarios. Here we we summarize our contributions. We introduced the challenging task of SPOL and identified associated challenges. We created a new SPOL dataset by combining existing video and sketch datasets with different styles and provided a benchmark with comparisons against frame-level baselines and model variance. We summarize our contributions. We introduced the challenging task of SPOL. We created a new SPOL dataset. We proposed SPANET. We summarize our contributions. We introduced the challenging task of SPOL. We created a new SPOL dataset. We proposed SPANET, a novel framework tailored for SPOL. We conducted comprehensive experiments. We summarize our contributions. First, we introduced the challenging task of SPOL. We summarize our contributions. We introduced the challenging task of SPOL. We created a new dataset and proposed SPANET, a novel framework tailored for SPOL. Lastly, we conducted comprehensive experiments. Thank you for listening our presentation. Thank you for listening my presentation.